So oftentimes it becomes necessary to define a function as what we call a piecewise. And what we mean by that is a piecewise function is a composite. We've seen composites before where we bring multiple pieces together. Is a composite of multiple functions. Let's break this down. Of multiple functions with non-overlapping domains. And that is key right there, that you cannot have pieces of the domain overlap for the different functions, because then you wouldn't really be a function. You would not know which of the pieces you'd be referring. So here's an example of this. Let's say that I have a function that is defined in 3 pieces. We're going to start by saying y is equal to 2, but only when x is less than 3. So instead of saying only when, we're going to kill that and just put a little comma and bring this together and bring that a little bit closer. But then we're also going to say y is equal to 3. We can do that between x equals 3 and x equals 4. And then we'll say that y is equal to 2x minus 3 for x greater than 5. And to make this look proper, I'm going to move the y to the middle. I'm going to use a left brace. And this is our first example of a piecewise function. Note that the domain of this piecewise function, let me change colors here, the domain is not all real numbers. For this domain, if I look at the values here, the domain is all x such that x is less than 3, or 3 is less than x is less than 4, or x is greater than 5. It's going to be gapping in some places, and that's okay. As far as the range goes, well, because there's a, we have to look at that on the graph itself. I really can't tell by this where it is and where it isn't. So this is the function we're going to graph. And what we are really graphing, and I want you to kind of see this, we really are graphing 3 lines. The first line is going to be the constant line y is equal to 2. But again, we're going to only graph for x less than 3. Then I'm going to graph the line y equals 3, but only for 3 is less than x is less than 4. Then I'm going to graph the line y is equal to 2x minus 3, but only when x is greater than 5. So that's what's going on here. Let's get the graph going. So put the grid down, zoom out a little bit, and I'm going to start by graphing y equals 2. So that's just a horizontal line. Let's get going a little bit thicker, and here we go. Graph y equals 2. There it is. But wait a minute, we said only for x less than 3. So I don't want to graph the entire horizontal line. What I do want to graph is what looks like a ray. I want to do that when x is equal to 3, and I want when x is less than 3 to graph this horizontal line. And x is less than 3, so I'm going to put an open circle there to indicate I'm not even really looking at that region. Okay, that is the line y equals 2. And I'm going to label that y equals 2, just to kind of keep that label going. Then if I graphed y equals 3, that's a horizontal line here, but wait a minute, I only want to graph it for 3 is less than x is less than 4. So here is x equals 3, here is x equals 4 on that line, and I would want to graph everything in between those and erase everything else. So that is the line y equals 3. And finally, we're going to graph the line y is equal to 2x minus 3. Now, typically, if you're not thinking too much, you may say, let's start graphing y equals 2x minus 3 on the y-intercept of negative 3. But the y-intercept of negative 3 is not in the domain. It says only when x is greater than 5. Only when x is greater than 5. Well, if I take 5 and I plug it in, 2 times 5 minus 3 is 7. That means that I can graph 5, 7 as an open circle and get that going. So let's graph that. In fact, I'm going to want to slide this whole thing over so I have some more space to graph 5, 7. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. That's going to be this ordered pair right there. And I would graph, let's move this out of the way. I'd graph with a slope of 2, because it's 2x minus 3, so up 2 over 1, point. I'll just put a couple of them down, and we can connect those. And I'm going to, because I had the other ones with really good lines, I'm going to connect this one with, with array as well. There we go. So this is the line y is equal to 2x minus 3. Let's delete all these little random dots. And just for the purposes of making this a clean graph for the image, I'm going to make the grid become a lot bigger now. Oops, let's try that again. Let's make the grid become a lot bigger. There we go. So now this is the piecewise function right here. Actually, I'll highlight it. And then we have a little piece there, and then we have a little piece there. But that's what we see. So that's the image. It's not a very clean image. It doesn't look as pretty as everything else. I'm next to the image. I'm going to bring down its domain. So slide this over here. Here's the domain. Let's see if we can state the range now that I've graphed this. If I look from the y perspective, there's a range value. It's all y such that I see that I have one here, y equals 2, or y equals 3, or, and then I can see this again is the ordered pair 5, 7, so y is greater than 7. And that would continue up. So let's try to do another example. We're going to graph f of x equals 3x plus 4 whenever x is less than negative 4/3, or negative 3x plus 4 whenever x is greater than negative 4 or greater than 4/3. Okay. Well, let's put a grid down. And here we go. So what happens when x is negative 4/3? Well, when x is negative 4/3, y is 0. Negative 4/3, 0 is an ordered pair. That's something that we also call the root, the x-intercept, or the 0. The value that when I plug it into the function gives me 0. I told you guys you can't graph thirds points, so we need to pick another point to start with. I don't want to start at negative 4/3. But let's try x equals negative 1. If I go negative 1 into that, I get negative 1, I get 1. That's not a point that's on the graph because that's to the right of negative 4/3, but I can certainly do a slope from there. I can put a point here at negative 2 and negative 2, and I can put a couple of points down here, here. So I'm going to erase this point because that's not a point that's on the graph. I'm going to try to connect these points, and as I connect with my, remember we can do half points as well, half point here, and half point here. As I connect those, I can kind of get an idea of where that negative 4/3 would be, and let's put an open circle on the x-axis, and then we'll connect the rest of the points. And then symmetrically, we're going to do the same thing. You'll see that when we start to graph it. If I plug in 4/3 into here, I get 0. So 4/3, 0 is an ordered pair. If I plug in 1, I get 1. If I plug in 2, I get negative 2. So 2, negative 2 is a better point to start with. But I can kind of visualize 1, 1 right here. Go down 3, right 1 for a slope. And same idea. Let's put our half points in here, here, here. And just try to extrapolate where that would be on the x-axis for an open circle at 4/3, 0. Let me try that one more time. It's not very precise. There we go. And then we'll draw from there and connect through all these points to get the image, and then erase this. So that's a piecewise function. If I want to describe its domain, it's all x such that x is less than negative 4/3, or x is greater than 4/3. And its range, if I just look at the y values, all y such that would just be y is less than 0. Okay, 2 more examples. Let's check one out where I say g of x equals negative 1/2 x minus 4 whenever the absolute value of x is greater than 2, or x is less than 5 whenever the absolute value of x is less than or equal to 2. So this is the first time we've seen a domain restriction have absolute value in it, and to make that happen we need to remember what this means. When the absolute value of x is greater than 2, that really meant that our x value could be less than a negative 2 or greater than positive 2. And whenever absolute value of x was less than 2, that meant that x was between 2 and negative 2. So knowing what those two mean means we're going back to chapter 2 and we're really reviewing what does absolute value mean for that. Okay. So let's put the grid down. And I'm actually going to graph the first line right here. I'm going to graph the entire thing before I decide which parts of the line to keep it. So I'm going to graph it at, let's see, y-intercept of negative 4, just graph it old school style, slope of negative 1/2, and this is part of why I made you guys draw every point on the graph, left to right, including half points. It's more important that you get that right than you actually learn how to draw a connected line. We get that you can do that. So as I zoom in, I'm going to draw all the little half points. It would take you less time to do that on actual paper than me on this. So please put all those points down. This also means that with those kind of points, you don't necessarily need to figure, we don't need to draw the entire line. I'm going to just to create the visual, but you shouldn't have to, because we're only going to keep a certain part of it. We're only going to keep the part that's less than negative 2 or greater than positive 2. So if I go to the part that is less than negative 2, well, at x equals negative 2, that's right here, and I'm going to put an open circle right there. I'm actually going to exaggerate that because I'm going to be able to erase within the middle, and I'm going to put an open circle here. And then let's take a small eraser and see if I can erase a little bit in the middle to make it an open circle. Let's erase a little of that to make it an open circle. I also want to chop this off here, and I want to chop this off, and I'm going to delete that, that, and that. And that gives me a line that is gapped between negative 2 and 2. Between negative 2 and 2, we're going to graph a different line. So I'm going to graph x is less than 5, or x minus 5. X minus 5 is going to be, let's change to orange, it's going to be a graph with a y-intercept of negative 5, down 5, put a point, up 1 over 1, and I'm not going to put every single point because I'm only going to do values in between negative 2 and 2. So I'm just going to put a few down. If I graph too much of it, that's okay, but I'm not looking to graph it with arrows. What I am looking to do is only graph between negative 2 and 2. And those are closed circles. So at x equals negative 2, we're right here. At x equals positive 2, we're right there. And I'm going to take my little eraser and erase, not the whole thing, but just erase this portion and this portion. Okay, now I can go back and cut that, cut that. There we go. That is graphing the line x is less than 5, or x minus 5, but only between negative 2 and 2. Only between those segments. Again, to be able to be a function, this thing has to pass a vertical line test. Oops, I didn't want to grab the whole thing. So if I draw a vertical line, and I slide it left and right, it's not going to be a piecewise function if it crosses through more than one point. So check that. That's actually working. I'm going to delete that because I think I shifted this line down. There we go. That's better. Check that vertical lines are not going to pass through more than one point. Okay, last example. We like these examples that are also step functions, so this is one that's going to be very similar. It's going to look tricky, but it actually is really simple. F of x is equal to 5, 6, or 7. 5 when x is less than 0, 6 when x is equal to 1, and 7 when x is greater than 2. So let's put a grid down. Since every one of those are constants, the only graphs that you should see are horizontal lines. And you're only going to see horizontal lines at x equals 5, x equals 6, and x equals 7. So I can kind of cheat a little bit and chop off the bottom part of this grid so we don't need to be zoomed in that far on it. And one way that I've had students do these is actually just graph all three and then erase. It's not quite as clean, but I'm going to do it here just for a visual. So I'm going to graph 3 lines, one at x equals 5, one at x equals 6, or sorry, y equals 5, then y equals 6, and one at y equals 7. 3 lines. And then we're going to decide which parts to keep. For the 5, we keep when x is less than 0. So less than 0. Let me do the little erase the whole circle thing in here so I get an open circle or something like that. Erase this part. Nope, just a little bit. And then we'll stroke erase the right, so that's all gone. That's x is less than 5. X equals 6 should never have been a line in the first place. That's just an ordered pair. Oops, sorry, x equals 1. So this means the ordered pair 1, 6 stays just as a single ordered pair, and the entire rest of that goes. And then finally, x is greater than 2 means open circle at 2. And I'm going to chop off the middle part here to make it an open circle. And then this, disconnect it from the left side, and then delete the entire left side to become that piecewise. So again, this is passing a vertical line test. We never described the domain and range of any of these, so let's go back up and do the domain of number 3, just so we can describe it. Looks like the domain, if I slide left to right, it's all real numbers. And the range, actually, if I slide up and down, also covers all real numbers. And yet it's broken in the middle, so it's just kind of weird how that can play out. In number 4, the domain is characterized by this right here, all x such that x is less than 0, or x is equal to 1, or x is greater than 2. So that shows the disconnections we have. And the range is only 3 values, and I don't need to put all y such that I can just list the 3 values, 5, 6, and 7. So that's it.